I am only mildly disappointed at this sentence.
This is not one of them.
I was gonna say, some of you are like, what do you mean? And then it's underlined right at the bottom of the exam. Meanwhile, though, you have something for me. Chapter 2, section 1, please.
Hey, I was not allowed to bring it down. You're right. Because this is what we need to know. It's like an old thing too.
I did post the key to the exam. If you have questions, please read that, then come talk to me. I would be more than willing to talk to you about why I took off the points I took off, and whether or not you disagree or agree with those. That's a separate issue. We can talk about whether or not you should get points back, but they have to be for legitimate mathematical reasons, not I really need a better grade. Because we all need better grades. But with an exam average in the mid-70s, it's a low mid-70s, it's not bad. I'm okay with that. I'm happy about that. Meanwhile, I want to keep talking about some of our stuff in sets, and it turns out that our idea of a function is really a set idea. So the question is, how do I get this as a set idea? Let me go back to algebra class. Cast your minds back. What's the definition of a function? A function from one set A to another set B. In algebra class, we were always dealing with functions of numbers. We don't have to. But even using that idea, what made an equation a function as opposed to something else? Seth? I get one back. It's precisely that. I get one and only one thing back. Normally, we write our function f as taking things from the set A to the set B. And we use that same arrow we've been using for the if-then, but that's not a requirement. And we can say f maps elements of A to elements of B. And we usually wrote this sort of functional assignment, f of A equals B. The word map here kind of indicates the set behavior. I have this set of things over here, and I transform it into this set of things over here. So you'll often hear these called transformations instead. As I said earlier, it doesn't have to be a set of numbers to a set of numbers. That's what we're used to when we think of a function going, say, from the real numbers to the real numbers. F of x is x plus 1. And sometimes we'll try and graph this thing. We'll write y equals, right? But what we're really doing is we're saying, oh, this y lives in this set, and x lives in this set. Our from and our to. Well, up here, those are A and B. So I need some names. Our from set is our domain. Our 2 set is the codomain. And I'm pretty sure those of you who have ever done functions are like, that's not what I'm normally calling it. Range. I want to be specific. So if we have A in A, then f of A is the image of the element A. And if I were to write that as B for some little b, I could also work backwards and say that A is the pre-image of B. So why don't I use the word range? Because what I really want to define the range as, I want to define the range as the parts of the set codomain that we hit. So I'm going to define this set, the set of B's that get hit by something. That's the range. Please notice this is a subset of B. It might be the whole set, but it might only be part of it. Strictly speaking, from an algebra perspective, let's consider this function. The function x squared. That takes in a real number. You take that number, you square it, you spit out a real number. Algebra class was a long time ago, man. But I remember this graph. This had a shape. What's the shape of the graph x squared? A parabola. And not just any parabola. This particular parabola opens upward, right? And it hits at its lowest point at 0, which means this only spits out numbers that are not negative, right? So the range of this function is not all of the codomain. The codomain was the set of reals, and my range is a subset of that. Questions? The domain and codomain of a function are an integral part of the function. If you change the domain or the codomain, but still have the same rule, technically, you have a different function. How is this one different? Ian. So I'm only dealing with integers, and that means that this is actually a very different function. As a matter of fact, it would have a completely different graph. We think, hey, this is going to give me a parabola, right? That's true here. But here, I get individual dots that are separated from each other. In this case, the range of f is separate numbers. And if I were to graph it, I would see a parabolic shaped set of dots. Bottom of page 157. Here. It's not a parabola because there's nothing in between my integers. It's a parabolic lattice, a set of dots. Sneaky. Questions? My domain and my range can be any sets. I just created a function this weekend. It assigned to each and every one of you a number. Right? All of the exam scores were between 0 and 110. I think the maximum possible on this exam was like 105. If I go back and look at the actual scores. But it assigns to each of you a number. The number you earned is your grade on exam 1. There's no requirement that my set strictly be a set of numbers. Every function that you write on a piece of code could operate on numbers, strings, Boolean values like trues and falses. You can have as your domain all sorts of options. Because we're on a computer, we code them numerically, but that's not required either. Questions? Reminders from algebra. If I am working with numbers, then I can add functions, I can multiply functions. And I remember doing this in my algebra class. If I have two functions, f and g, that start in the same set and go to the real numbers, then I can write f of x plus g of x, or I can write f of x times g of x. I'm either adding numbers or multiplying numbers. We'll define the function f plus g. We'll define the function f times g this way. We can do division, but we can only do division when we're not dividing by 0. So that kind of screws me up a bit if one of the real values I can take on is 0. So I tend not to do that. If I have a function from A to B and I have a subset of the domain, I could define all of the values that S is mapped onto, kind of like we did with the range, right? But instead of doing the range, I'm just going to do this little piece. F of S is the set of values F of little s, so that S is in capital S. This is a subset of the range, therefore a subset of the codomain. So if I go back and I think about our square function, let's go from the integers to the integers. Then I could say, oh, here's a set. What's f of s?
Four, 1, 9, 25. I think that's a 0.
Yes, that's a 0.
And 1,
0 squared is
0. Other way around.
absolutely. By the way, if I had also had, say, a positive 2 in S, I hit 4 twice. Do I have to list it twice? Sets are unordered. And I don't have to have repetitions. I can also work backwards. And I could say, okay, here's a set. I'd like the pre-image. Oh, wait a minute. The hell is that? We used this word pre-image before. I don't necessarily have an inverse. I need to figure out what that definition means. But if I think of it as working backwards, I'm over here in the codomain. I want to know, hey, what hit those things? The pre-image of T is a subset of A. And it is the set of A in A such that f of A is an element of T. The reason I don't want to use the word inverse is due to something I will come up with in just another couple minutes. There's a very technical piece about being an inverse. But now I just need to know, hey, my function is f of x equals x squared. F of x equals x squared. So really what I need to do is I need to solve these equations. And write down all the things that are solutions here. Which in this case gives me more items. That's okay. More questions. Talk to me, people. You've seen all of this in algebra class. I'm just abstracting it a little further. So I need to talk about some properties of functions to try and nail down this idea of an inverse. And to do that, I need to define a function is 1-to-1 or injective if, well, I need to figure out what that means. But just from the word, a 1-to-1 map. What does that mean?
But now it has to match little a1 to little b1, and it has to go, every single one has to match.
I don't have to know that they go in order. But if A1 goes to B1, then nothing else can go there. 1 to 1. If A2 goes to B17, it's the only thing allowed to go to B17. All right, wait a minute. No two things can hit the same thing. I can write this as a universally quantified statement. For all X in A, for all Y in A, if the outputs are equal, then the inputs must have been equal. The only way to land on the same thing is to start from the same place. Ooh, wait a second. Somebody, what's the contrapositive of this? You thought I'd get away from it. No, not ever. What's the contrapositive of that sentence?
That if it's f of x equals f of y, then it's not x equals y?
That's not my contraposition. Yeah, I was gonna say that's contradiction, Roman.
Not x then y, or if it's not x equals y, then it's not f of x. equals f of y.
Different starts must go to different places. Okay. I think I get why they're calling it an injection. Each one is in to one and only one thing. I see little arrows in my head. I have my domain over here, my set A. I have my range over here. And I can make a one-to-one function like that. Every element in A goes to one thing in B. And none of the pairs of elements in A go to the same thing in B. This function is one-to-one. But same set A, same set B, this function is not one-to-one. Because both f of C and f of D are the same, but the starting points aren't. Okay, I think. Questions? Talk to me, please. What do you got? Make sense? Let's think about one of the functions we were just dealing with. Let's think about the x squared function. Is x squared one-to-one? Seth, you're shaking your head. Tell me why.
Example 2, -2.
Two different values hit the same thing. Absolutely. And all it takes is one counterexample for a universally quantified statement. More questions or comments? Over in Southside Flats, there's a kitchen store called Sur la Table, on the table. That's how I remember the damn word all the time. Surjective means on to. I want to be on to everything in my codomain. This is the difference between range and codomain. In order for me to say, oh, you've hit everything that is over there, that's an on-to function. Means if you pick any element in B, I had to hit it with something.
This be like it has to be continuous?
I didn't say anything about any of that. Our function x squared from integers to integers has nothing to do with continuity.
Right.
Well, because I'm talking about z, right? And it jumps between every one of those points. If there are jumps all over the place, it's not continuous. So as much as I like the idea of continuity from calculus, that's an even more restrictive condition that we're not there yet. And that only works for functions that are numbers. These work for any function. Okay, so how would I say this? How would I say this in that sort of conditional statement that we did earlier? Okay, for anything in the range, there is an element in the domain so that we hit it. If you look at the picture right above this, that function is not onto. Why? This function right here. Why is this not onto? Don?
There's like 2 and 5 don't have.
Nothing hit that. There's an element in my codomain that is not hit. Now, I'd be hard pressed to make a function that was onto here. Why? Why would I find it very difficult to make an onto function here?
There's 4 elements in set A, and there's 5 in set B.
And I can only go to one thing, right? Exactly one element of B is assigned to each element of A. I can't hit 5 things with 4 arrows. But that's onto. As a matter of fact, that's onto. But there's a substantial difference between those two. Our other condition. The top picture is 1-to-1. The bottom picture isn't. So these conditions are independent of one another. If I have both conditions, an injection and a surjection, I'm going to call it a bijection. Functions that are both one-to-one and onto. Questions? Injection, one-to-one. Like the little needle is going across, my little arrows only hit one thing. And then onto it covers everything. I'm on the whole table.
So we know that if F is injective and the cardinalities of two set of the same, does that automatically mean it's surjective?
If it's one-to-one and they're the same size, is it automatically onto as well? Yes, if those sizes are finite. Infinity is weird. That's Friday. Ready for the better part? In a finite set, being one-to-one automatically gives you onto, and being onto automatically gives you one-to-one. You get one, you get the other one for free. But only when my sets are finite. We'll make more hay out of that on Friday. More questions? Yes, ma'am.
So the top one,
Yes.
like, since C and D are both touching the board, why can't we just have B touch two and C?
Ah. Because if B touches, let's say B touched two things, right? I got to go all the way back to the very first thing I wrote down. It assigns to each value on the left one thing on the right. So if I go from one thing to two different things, I don't have a function anymore. I have a relation, like we were talking about as the subset of the cross product, the Cartesian product. So that breaks the idea of it being a function.
Thank you.
Oh, you're very welcome. More questions. It is reasonable to want to try and assign something to every one of those, even if you had to assign one to more than one thing. We call that a relational idea, and we'll have to study it differently than we study functions. And those are harder to define in rules unless we write them implicit. So, we go back to algebra class. Or trig class, depending on what you had last, most recently. I know that graph. What's that the shape of?
Unit circle.
It most certainly is a unit circle. A circle whose radius is 1, whose center is the origin. If I try and write that y equals, what's the problem? If I want to write this as a function, I should be able to write it y equals. Now I have a rule to tell me what the y value was. Exactly. So if I'm gonna have multiple outputs for each input, then I don't really have a function. I have a relational equation. And in the graph, we used to do this, again, I go back to my algebra class, we used to draw vertical lines. And say, oh, if your vertical line touched it more than once, then you had two different y's for the same x. That wasn't a function anymore. So it's really the vertical line test, but I wrote it with little arrows instead. Questions? Yes, I agree with you. This is abstract and therefore weirder. When we are dealing with functions whose outputs and inputs both are sets of numbers, then we can talk about direction. So, let me think about a function from the reals to the reals or from some subset of the reals to some subset of the reals. I want to talk about real numbers here. F is strictly increasing. What does it mean for a function to increase? Don't think about any sort of mathematical idea. Think about a picture. What does it mean to be increasing? As I go from left to right, I go up. As I go from left to right, my y values go up. I like it. And if you get rid of the word strict, then this becomes less than or equal to, and so does this. So what's decreasing? All I have to do is turn this one around. I'm still going from left to right. But as I go from left to right, I go down instead of up. And the word strictly, what's the word strictly going to do there? You got it. Why would I mention this? If f is strictly increasing or strictly decreasing, then it's 1 to 1. I beg your pardon? Why is that true? Seth?
We never allow x to be equal to y.
And to be 1 to 1 means that different inputs go to different outputs. And the only way to get back to have the same y value, to have the same output, is to go up and come back down somewhere. Wait, increasing means you can't come back down. Decreasing means you can't come back up. You're going one way. You can't turn around and hit the same horizontal line twice. By the way, this idea, being either strictly increasing or strictly decreasing, is referred to as monotone. A function is monotone if it's either always up or always down. I wrote myself a note. So let me think about what we just proved, even though I didn't actually write down a proof, I just kind of spoke my way through it. If I want to show a function is one-to-one, I want to show that if you had two things that were the same, then they actually had to come from the same spot. Or if I had two things that were different, they had to go to two different spots. Similarly with showing that it's onto. If it's onto, I want to find, oh, I'm over in the range. How do I get back to the domain? Find the element. That's a constructive proof. Page 153. You should put a post-it flag on this box on page 153. How to show something is one-to-one. How to show something is onto. If I'm going to ask you about functions, I'm going to ask you to prove these sorts of properties. That's what we need. Okay. I've managed to avoid the word up until now. What's an inverse? A function only has an inverse if it is a bijection. Now, the real question, why do I need this to be one-to-one? Why do I need this to be onto?
You're gonna switch the elements of A and B, and if you didn't have them connected one-to-one, then whenever you switch them, it could be B to A1 or B to A2.
So if my function's not one-to-one, then when I turn it around, it's not a function. If my function's not onto, when I turn it around, I have elements that are in the domain that are undefined, right? So this is a problem. The only way I can make it match is if there is a one-to-one and onto, then I can literally just turn the arrows around. And instead of going from left to right, go from right to left. But that only works when we have one-to-one and onto behavior. And Ian, that's why I shied away from saying, well, we have the inverse of x squared. X squared is not one-to-one. Okay, this is me being a pain in the ass mathematician here. When I draw that graph of x squared, I get a parabola. Yes? Well, when we take square roots, we only take the square roots of things that are positive. I've changed the domain to only look from 0 to infinity. And on that part of the graph, this graph is strictly increasing. And if it's strictly increasing, it's 1 to 1 there. So I can have it be 1 to 1 and onto on this side. And that will work. And that's where I get x squared and square root of x being inverses. But it's not on the whole parabola, it's only on part of it. And we cut it, and then made the choice that we wanted the positive part. You could just as easily cut it and make the choice that you want the negative part. And that's why there's the plus or the minus outside the square root. Because it's not part of the square root itself. The square root always returns the positive part. These, by the way, are called the branches of the square root function. They're the positive branch and the negative branch. Branch points for all sorts of functions was part of my PhD in mathematics. Blah, blah, blah. So I can only do an inverse when my function is 1 to 1 and onto. But if I have functions that go from numbers to numbers, I could take the output's a number, right? I might be able to put it into another function. If I have 2 functions, f1 and f2, then I can take the stuff that comes out of f1, that's in the set B, and I can put it into f2. So I would be doing first f1 of something, right? That would give me a little b. And then I would be doing f2 of that little b, and that would give me a little c. In my pictures, A, B, C, this is f1, this is f2. I want to cover that middle step up and go directly from A to C. That function is the composition f2 composed with f1. Notice the order. I'm working from the inside out. It's really f2 of f1. Because that's f2 of b, isn't it? f1 of a, that was b. Aha. So it's from the inside out. We read this way. Almost always, order matters here. So f2 of f1 is different than f1 of f2. Because I am a math geek, there are a number of functions that we define here in this section that are fairly useful. We define the floor function and the ceiling function, where you round down or round up. The floor function rounds down. The greatest integer less than or equal to x. So the floor of 2 is 2, and the floor of 2.1 is also 2. The floor of -1 is -1, but the floor of -1.1 is -2. I go down to the next integer. Floor. So what do you think ceiling does? Rounds up. I'll use the symbol with a little roof instead of a floor. Least integer greater than or equal to x. There's also an integer function that is not n, that's n factorial. And it's only defined for non-negative integers. And n factorial is n times n minus 1 times n minus 2 dot 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 times 3 times 2 times 1. With one exception, 0 factorial is defined to be 1. By the way, just to show you, these numbers get really big really quick. 4 factorial is 24. 5 factorial is 120. 6 factorial is 720. 9 factorial is 362, 280. These numbers get really big really quickly. Your calculator, your graphing calculator, won't hold 70 factorial. That's huge. There are lots of other functions in our textbook that are useful. Floor, ceiling, and factorial will be the 3 we use most often. I'll talk more about functions and more about specific behaviors on Wednesday. I will see you all there. If you came in late and I still have your exam, come get it from me. That's how I'm taking attendance today. If you have homework, come give it to me.